What if a comet passing through our solar system is not just older than Earth, but older than the Sun itself? That is the extraordinary possibility raised by new research on 3I/Atlas, one of the rare interstellar visitors ever detected. Most comets we know were born with our Sun. They belong to the same ancient family that produced the planets, moons, asteroids, and frozen debris of the solar system. 3I/Atlas appears to be different. It seems to have come from somewhere else entirely, carrying the chemistry of another stellar environment into our cosmic neighborhood. That alone would make it exciting. But what really has astronomers paying attention is the suggestion that some of its material may preserve conditions from before our Sun even formed. The clue comes from isotopes, especially unusual nitrogen and carbon ratios reported for this object. Those ratios behave like chemical fingerprints, helping scientists infer the temperature and environment in which material formed. To see why this matters, we first need to understand what an interstellar object actually is. An interstellar object is a body that did not form around our Sun, but was ejected from another system and sent drifting through the galaxy. Astronomers expected such objects for years. Young planetary systems are violent places, and giant planets can fling enormous numbers of icy bodies into interstellar space. But finding one is hard. These objects are faint, fast, and usually discovered only when they are already rushing through the inner solar system. That is why the first detection in 2017 was such a shock. Oumuamua became the first confirmed interstellar visitor, and its strange appearance launched years of debate. Then in 2019 came 2I/Borisov. Unlike Oumuamua, Borisov looked more like a familiar comet, giving scientists their first clear glimpse of icy material from another star system. Now 3I/Atlas may be opening a new stage in that story. Instead of simply proving that other systems produce comets, it may be showing that some interstellar objects preserve matter from an even deeper cosmic past. The name itself tells us a lot. The 3I means it is the third confirmed interstellar object, while Atlas refers to the survey that discovered it. Atlas is part of a growing network of sky surveys that repeatedly scan the heavens for moving targets. These systems watch for asteroids, comets, and anything unusual that changes position from night to night. Once 3I/Atlas was found, astronomers moved quickly. Interstellar visitors do not stay long, and every observation matters before they vanish forever into the dark. So what makes this object special? According to recent reports, its nitrogen and carbon isotopic ratios are unusually high compared with what astronomers often see in solar system material. That may sound abstract, but isotopes are one of the most powerful tools in planetary science. They are slightly different versions of the same element, and the balance between them can preserve a record of ancient physical conditions. You can think of isotopes like an accent in a voice. Two objects may both contain carbon and nitrogen, but their isotopic accents can reveal very different birthplaces. In this case, the signal points toward an extremely cold and ancient origin. If that interpretation is correct, at least some material inside 3I/Atlas may have formed in a primordial environment that predates the stable planetary system it eventually came from. That is where the headline idea comes from. The comet itself may not be a perfectly untouched time capsule, but parts of it could contain matter older than our Sun. That is a huge deal, because comets are among the best natural archives in space. Deep inside, they can preserve ices, dust, and organic compounds that planets usually erase through heat, geology, and chemical recycling. If 3I/Atlas really carries such ancient material, then it is more than a foreign object. It is a messenger from a time before our own solar system existed. And that changes how we think about planetary science. Usually, when astronomers study distant star systems, they must do it indirectly through starlight, orbital wobbles, and computer models. An interstellar comet changes the game. Suddenly, some physical debris from another system has come to us. We still cannot hold it in a laboratory, but we can analyze the light reflecting from it. From that light, scientists can infer composition, chemistry, and clues about the environment where it formed. That opens a remarkable possibility. If more interstellar objects are discovered, astronomers may be able to compare how different planetary systems build and eject comets. Maybe some systems produce more carbon-rich bodies. Maybe others preserve colder, more nitrogen-heavy chemistry than the early solar system did. If so, interstellar objects could become a new kind of comparative planetology. Instead of comparing only planets around other stars, we could compare the frozen leftovers of planet formation across the galaxy. There is also a deeper connection to our own origins. The solar system formed from a cloud of gas and dust, and many of Earth's ingredients came from material older than the Sun itself. So when scientists study an object like 3I/Atlas, they are not just learning about another star system. They are also probing the long ancestry of matter, including the raw ingredients that eventually became worlds, atmospheres, oceans, and perhaps life. That is why isotopic measurements matter so much. A tiny chemical ratio can connect a small icy body to events spanning billions of years. One spectrum from a faint comet can point back to frozen molecular clouds, young stars, migrating giant planets, and violent gravitational ejections. Few scientific tools let us jump between such small and such enormous scales. Of course, caution is essential. Rare objects often inspire dramatic interpretations, and the data must be tested carefully. Astronomers will compare 3I/Atlas with known solar system comets, refine the measurements, and check whether the isotopic signal remains strong under different models. Exciting evidence is not the same thing as final proof. That lesson matters, especially after the frenzy around Oumuamua. Public imagination can sprint far ahead of the data, so scientists have to stay disciplined about what the observations truly support. Even so, the cautious version of this story is still amazing. At minimum, 3I/Atlas is another confirmed visitor from beyond the solar system, and its chemistry already appears unusual enough to deepen the mystery. And if the older-than-the-sun interpretation survives scrutiny, then this object becomes one of the most ancient messengers ever observed in our celestial backyard. It would mean that the Milky Way is not just full of stars, but full of wandering relics that carry memories from one stellar generation to the next. There is something beautiful about that idea. The galaxy is not made of isolated systems that keep their contents forever. Stars are born from shared reservoirs of matter, they lose material back into space, and some of that material travels for ages before crossing the path of another system. Interstellar objects are evidence of that cosmic exchange. That perspective makes the universe feel more connected. A comet passing near our sun may have begun its journey around another star, or even in the cold cloud that existed before that star fully formed. In other words, 3I/Atlas may be showing us that the boundaries between star systems are more porous than they seem. Matter moves, mixes, and sometimes arrives carrying a record of places we could never otherwise visit. There is also a practical future to all of this. The more interstellar objects we discover, the more realistic it becomes to design a mission that could intercept one. Imagine a spacecraft launched quickly enough to photograph an interstellar comet up close, sample its dust, or perhaps one day return material to Earth. That would be one of the most scientifically valuable missions ever attempted. The challenge is timing. These visitors are usually found late, and they move incredibly fast. To catch one, we would need better surveys, faster alerts, and mission plans ready before the next object appears. But that idea is no longer science fiction. As telescopes improve, interstellar discoveries should become more common. And once scientists have a larger sample, they can start asking statistical questions instead of treating each object as a one-time miracle. Are interstellar comets usually chemically different from solar system comets? Do they come mostly from young chaotic systems, or from mature systems with long histories of planet scattering? Are some of them fragments of planetesimals, while others are nearly pristine frozen relics from the earliest stages of star formation? Those questions connect planetary science directly to the larger evolution of the galaxy. That is why 3I/Atlas matters. It turns the idea of distant star systems into something almost tangible. Not just a dim signal around a faraway sun, but a real object crossing our own sky, carrying chemistry we can decode. It reminds us that the history of the universe is stored not only in galaxies and black holes, but also in small icy travelers that preserve ancient memories. So, is 3I/Atlas truly older than the Sun? The honest answer is that the evidence is exciting, plausible, and still being tested. But even that uncertainty is thrilling. Science is unfolding in real time, and every new observation could sharpen the picture. For now, one fact is already clear. We are entering an era when pieces of the galaxy no longer feel completely out of reach. Sometimes, they come to us. And sometimes, they may be older than the star that gave us life.